Good morning and welcome to the second video of Thursday of week 4 of your Physics 5 a day. Yesterday we saw that if we have a wave source that's moving towards us or away from us, then the wavelength of the wave that actually reaches us is going to be different than compared to if the wave source wasn't moving. And this is called the Doppler effect, and we're all very familiar with it with sirens. We all know what it sounds like when a siren goes past. And that is the Doppler effect with sound waves, and you can think of it as the waves being squashed as the siren comes towards us and being stretched out as the siren moves away from us. And this is the formula that tells us how much the wavelength is going to change, and it depends on, in this situation, it depends on the speed of the car relative to us and the speed of sound in air. We also saw that you can have the Doppler effect with light as well. So if we have a nearby galaxy that's spinning, well, the stars on one side of it will be coming towards us, and so the light waves from those stars arriving at Earth will have a shorter wavelength, and we call that blue shifted light. And the light from the stars on the other side of the galaxy that are moving away from us, well, the light from them, when it arrives at Earth, that's going to have a longer wavelength, and so we call that light redshifted. And so this is called the relativistic Doppler effect, and this is because the stars are actually moving through space relative to the Earth. Now, interestingly, when scientists measured the wavelength shift of the distant galaxies, they measured what the change in wavelength was, and they found that all of the light from all those distant galaxies, it was all redshifted, and then they used it to work out how quickly those galaxies were moving away from us, and they found something else interesting. They found that the speed that a galaxy is moving away from us, which we call its recessional speed, is directly proportional, would you believe, to how far away it is. And there's a lot of scatter. This is sort of, I'm trying to show the original data here a bit. There's a lot of scatter, but it's a definite linear trend through the origin. So all the distant galaxies are moving away from us, and if they're twice as far away, they're moving away from us twice as quickly. Now, before we think about what that means, let's just note that if something is directly proportional to something else, then it's equal to a constant times something else. And in this case, that constant is called the Hubble constant. That's the Hubble constant there. And that's obviously the gradient of this graph. Okay, but what does it mean if all the distant galaxies are moving away from Earth, and if they're twice as far away, they're moving away twice as quickly? Well, there is in fact a really easy way to explain why that's happening. Here, if we take a look at this elastic band, so A is going to be Earth, and I'm trying to line that up with 20 centimetres there. And so then we've got galaxy B, which is at about 22 centimetres, and galaxy C, which is at about 24 centimetres. Okay, I'm going to try and keep Earth, which is A, I'm going to try and keep Earth still. And now watch what happens if I stretch the elastic band so that galaxy B has moved 1 centimetre. Oh look, galaxy C has moved 2 centimetres because it's twice as far away. So the pattern that we observe here can be explained really easily if the actual space itself is stretching. If space itself is actually expanding, that explains this pattern. And so that's why Hubble's law and the redshift of the distant galaxies is evidence for the expansion of the universe. Okay, while that's quite mind-boggling, the questions on Hubble's law tend to be much more straightforward. So here's an example. You're going to want the Doppler formula for this first part of the question. Okay, so this is the original line. This is the line in the lab, so we kind of treat that as initials, and then this is the one that we're detecting from the galaxy. So our change in wavelength is going to be 4.58 nanometers. And just check your sign here. You know that it's a distant galaxy, it's moving away from us, so the wavelength should have got longer, and so that's positive, that's right. And I haven't left any space for it, so I'm squeezing it in up here. Now notice I haven't bothered with the 10 to the minus 9 for the nanometers, because I know that both the top and bottom are nanometers. They're just going to cancel out. And also notice that that lambda on the bottom, that's the lambda if you were in the lab. So if the light wasn't moving relative to you. And I've got 3 significant figures, so rounding to 3 sig fig at the end. But then we want to convert to kilometers per second to put it into the table. I get this, which you can see is the right order of magnitude. That looks to be about right. And then when I plot all my points, it's looking like this. And remember, we want a straight line through the origin. We know our line should go through the origin here. Normally it's a massive no-no to force your line through the origin if your points don't suggest it. Although ours do, but in this case there's a large amount of scatter for this data, and that's correct. That's what the data really looks like, and so the mark scheme specifies that you have to make sure your line goes through the origin. And so the gradient is going to be the Hubble constant, and to 2 sig fig, because this was to 2 sig fig, we get 74 kilometers per second per megaparsec. No need to change the units.